I would also like to welcome you and also thank you for your presence here. It's really a pleasure for me to be here and been working on this 10th edition of the Faculty Summit. Actually, it looks like yesterday when we started in Embu back in 2005. So I've been really very honored of being the chair of these 10 events in the past 12 years. So it is my pleasure now to introduce our next keynote speaker, Professor Carlos Eduardo Pedreira. Professor Carlos Eduardo Pedreira is with COPY, Systems and Computer Engineering at the Federal University of Rio de Janeiro. He holds a Bachelor and Master of Science degrees in Electrical Engineering from the Catholic University of Rio de Janeiro. He received a PhD degree from Imperial College of Science, Technology and Medicine, University of London. He's also a visiting researcher at the University of Salamanca, Spain, since 2002. He was the founding president of the Brazilian Society of Neural Networks, presently the Brazilian Society of Computational Intelligence. He's a member of the Euroflow Consortium Board and received the Santander Bank Award of Science and Innovation back in 2006 and the Nicola Albano Prize, Brazilian Society of Pediatrics in 2010. Please join me welcoming Professor Pereira to the stage.
Thank you very much. Okay, I will talk a little bit about my vision of computer medicine, computer modeling medicine, and future perspectives in this area. I have to get accustomed with this. I started showing something that's a pattern, a US pattern of the magnetic resonance apparatus. I'm showing this because we have sometimes the impression that this sort of apparatus always existed because it's so common nowadays. And this is the pattern, and the pattern is from 72, what means about 40 or 50 years ago. It's quite recent from the historical point of view. And just in 77, it took 5 hours to generate the image, just to have an idea. And the first, and the first commercial device was produced just in the beginning of the 80s. And then I moved to flow cytometry. A large part of my presentation is related to flow cytometry. And just to say that flow cytometry is the way that leukemias and lymphomas diagnoses are made all over the world. So it's a quite important thing. These are the first flow cytometers on the beginning of the 70s. And I have to make attention to this company, this Becton and Dixon, a BD, because I'm going to come back to this company at the end of my talk. This is the first apparatus. And then this is the modern one. This is exactly the one that we have in our laboratory nowadays. And let me explain in 2 slides a little bit how this machine works. Basically, we have a lot of have cells in suspensions here marked with monoclonal antibodies. And then these suspensions come up again, back. Come up by a negative pressure and then pass to this laminar flow. So we have a laser light in here. And then the first measure, that's more or less the size of the cell. And the second physical measure is the side, or what we call side scatter for SSE. And this is the light that goes laterally. And a part of that, you can see that here we have represented the monoclonal antibodies. And this, what we're going to read in here are the colors. So the result of that is that by flow cytometry, we can measure a lot of parameters, about 30, and millions of cells. And the important thing is that the measures are done in each cell. So I have about 20 or 30 measures for each cell. This results in a huge amount of data. And this data have to be processed in an intelligent way. So I start with the resonance magnetic apparatus, and then I went on the flow cytometry, just to say that this apparatus that the medicine or the engineers have given to medicine are returning to the computer science people a lot of data. And we have to process this data in an intelligent way in order to extract the information that is needed. And then we come to big data, but in this case, big biodata. Just to have an idea, the typical flow cytometry exam will produce about 400,000 events, cells in this case, with 30 measures in each. And in a different exam, I'm going to talk about this too. We have 5 million events or 5 million observations from the statistical point of view with 12 attributes measures in each. So it's really big data. Just to have an idea of the sort of problem that we have, I was talking about 30 measures. What means that we are in the R30 space. And just to have an idea, this is real data. This is real data. Each point is a cell. And we are seeing here just in 2 dimensions, CD23 and CD32, or 23 and 23, just 2 different attributes. So this data is on a 30-dimensional space. And just to see the complexity of the problem, we are just what happened just in 2 of these 30-dimensional space. I have here, in this case, 3, back again, 3 populations and a lot of noise around. And the challenge is to identify these 3 populations in the middle of this noise. Just remember that the real problem is on the 30 dimensions, and we are just seeing 2 of these 30 dimensions in here. I would like to go now to a different problem to talk a little bit on the protein world, and then we have different challenge. Just well, my table is in Spanish, but I think it's okay. Here we have about 40,000 proteins, sometimes more, just measuring 51 patients plus 8 healthy controls. And these are the 3 questions that we would like to solve or to answer in this case. First question: which proteins may differentiate healthy patients from pathological patients? Second question: which proteins may differentiate metastatic from non-metastatic patients? And the third question: which proteins may predict evolution of these patients? Just observe here that we have for each of the patients that are on the columns, which ones are metastatics and non-metastatics, and assigned for evolution. This table continues, of course, on both ways. And the problem with this type of problem is that we have thousands of attributes and few observations. It's the reverse problem if I compare to the normal problems that we are accustomed in machine learning. Normally we have a lot of observations and few attributes. Here we have thousands of attributes and just few observations. And the key problem here is, in fact, a problem of selecting attributes, because the questions in this case is always related to which protein is differentiating one situation for the other. So I may translate this from the machine learning point of view in selecting attributes. And but it's a very difficult problem, a very hard problem, in the sense that I just have few patients, because these exams are expensive, because this disease is rare, and so on. And I have to select from thousands to end up in this problem. This is a real problem. Our aim is to end up with about 200, between 100 and 200 proteins that may differentiate the three questions that I put before. Just to show, compared to cytometry problem, a different difficulty in these problems that we may call in the family of the big data or big biodata problems. And now we go to projection. And I'm going to talk a little bit about projections in 2 dimensions. Of course, in this case, I project to see, to take the decision by seeing. And this is a very, very nice illustration that we may project from the high dimensional space in the 2D dimensional space in very different ways. And depending on the way that one projects, the result is completely different. Why and when we should project in 2D? First, to go in a different way, many times we are trying to get automatic ways of doing things. And in this case, we are going in the opposite direction. We don't want to take the decision in an automatic way. In fact, what we want is to provide decision support, and the final user, the decision maker, is the one who is going to take the decision. And when this problem is relevant, in medicine is very, very relevant. First of all, for ethical reasons. In many cases, the system cannot give the diagnosis. The diagnosis is to be given by a medical doctor. And the second and very important thing is that in medical problems, this is very frequent, that many times we want to add individualized information. In the medical problem, it's the case that where the doctor knows that this patient has a particular condition, and it's a mistake to try to model everything, to try to put everything inside the model. Because in the end, this should be a so complex model that would not work in practice. So it's a way, by taking the decision by a visual decision in a 2D plot, it's a way that you leave space for extra information to come in for individual, in the case in medicine, individual patients. This is not restricted to medicine. In many financial areas, also people does not like to take the decision just blind, just without knowing why this decision is taken. So it's very relevant to think in providing decision support for the final user, and one very interesting, one very efficient way of doing this is to project data from the high dimensional space in 2D, where we can see and take the decision by seeing. Projecting data in R2 is equal to be able to take the decision, and the traditional methods are the PCA and the MDS, multidimensional scaling. And I think that these methods have survived for many years, for decades. And I think there are many, many methods now published. And I think that most, if not all, these methods are in fact variations, adaptations, and of the original PCA and MDS. They are very similar, and I think these two methods are the original ones, and many things that we have now derive in some sense for these two basic methods. And in fact, the difference between our algorithms and methods to project data from high-dimensional space into 2D basically are related to the function to be optimized, because of course, if one project data from a high-dimensional space in 2D, something is going to be lost. So basically, these methods are methods that are minimizing what one loses by projecting in 2D, and secondly, by the methods that are used, the optimization methods. So the two key issues that differentiate methods of projecting in 2D are really related to the optimization algorithm. Some are more efficient than others, and the loss function that is used to make the projection, and this loss function is really related to what one wants from this projection. So we have to choose this criteria to project data, and one way to choose this is to preserve the distance structure in the original space. So this means to try to have a projection in 2D that mostly reflected the structure of distance in the original high-dimensional space. A different way is to project trying, I think I need my sunglasses here. Thanks. And the second way is to try to produce compact and well-separated groups in 2D. Of course, with the second criteria, I'm just looking on classification direction. First question is, I'm just going to talk a little bit about PCA and MDS in 2 slides. The first question is why to use variance-based methods like the PCA. The PCA is based on the variance of the data. A good answer for that is that because we know a lot about the optimization methods. There are a number of well-tested algorithms, and the second is more important than the first. It works quite well in many practical situations. This is like the k-means. It's a very old method, and people try to beat these traditional methods. And if you have a good k-means, a good PCA, it's very difficult to beat them. It works quite well in many situations, but sometimes it's not what we want. And in some problems, especially the PCA, can give us some trouble. Just observe this figure. What's going to happen, for instance, the population blue and green are very well separated in the direction A, but direction B would be a disaster for blue and green. Direction A is very good for blue and red, but not so good for green and red. And so on. So depending on the variance of the data, PCA may not work. And basically, PCA is not going to work when the variance of the two populations, I'm talking of 2 or 3 populations, is smaller of the variance of one single population. In the sense that as PCA is a non-supervised method, we are not seeing the red, the green, and the blue that we are seeing in this figure. So the method is going to see the whole variation of the two data sets, And sometimes the inside variation in one of the clusters is very, very important. And then this is what is happening here in comparison of the whole data. Just going to the second approach, the MDS. The idea on the MDS is basically it's quite old methods. I think the first papers was published in the 60s. And the key idea is very simple, is to project basically the data in 2D, mostly maintaining the original structure of a distance in the original high-dimensional space. And technically the difficult thing on MDS, and it's all the variations of the methods comes from this, is that this is an optimization problem that's not trivial. And of course, this problem has never, apart from very particular situations, this problem would have an exact solution. Recently, a few years ago, it came another idea that's a supervisor MDS. And the key idea is to give to the algorithm the label of the classes before starting everything. But this has a very important setback. And the setback is that one has to decide the amount of supervision. And this is a very difficult parameter to adjust, because if one gives a lot of importance to these parameters, since we know the class in advance, the generalization is going to be very poor, because in fact we are giving a lot of information about the classes. So it's very difficult to adjust the amount of supervision concerning labels, concerning classification that one want to give to the method. An interesting solution for that, and we are working with this solution, is just to project the data, taking in account the distance that the observations have to the prototypes. So I supervise the method in the sense that I have to establish prototypes in the high-dimensional space first. I project these prototypes to the smaller space, to the R2. For instance, if I just have 3 classes, this is a closed form problem. I don't have any optimizations to make, because I just take the plan in the high-dimensional space and then I have the projections out to space. And then I project the observations, taking into account the relation of the distance to the observations to the prototypes. So I try to reproduce in R2 the structures of distance between the observations to the prototypes, and not among all the observations. This has a lot of advantages. The first thing is that classification is on the problem, directly on the problem. I don't have to choose the amount of observation. I'm again back. And so the main parameter that was a problem in the supervised MDS, now we don't have it. I'm going to a different problem now. I'm just going to look a little bit inside the data. I'm going to look inside the data, trying to find internal structures. That's what we call the local global approach. And just 2 slides to give an example of that. What we do here is that we start with that, and then we have 2 prototypes here. And by that point, I have a lot of points in this area that, of course, are red, a lot of points in this area that, of course, are blue. And then I take these points out because I know already the classification. And then I have this area, and I go again with this area, I subdivide, and I subdivide again. The main advantage of this sort of approach is that when everything is done, I know not only the classification, but I know the risk of classifying the points in that area. For instance, in the area that are in the upper part and the lower part, that everything is red or everything is blue, I can classify in there, and the risk is very low. If I am in this area around the middle where the blues and reds are really mixed, I can still classify in here, but I have a different sort of risk. So I can attribute the different levels of mistake to different areas of the space. So now we are back. We are back to cytometry. And I want to talk a little bit of two different possibilities. One, I have the full information. That means that I have 12 attributes per cell, 5 billion cells. And in the second approach, I'm going to use the information of the mean of the cells. So I have few points and I have more attributes. Two different ways of looking at this problem. This first approach is related to using, I'm still mixing up here, the full information. So I have all the cells and not the means. And this has a very important application in the area that we call minimal residual disease. This is used just to try to identify a very small quantity of cells after chemotherapy normally, and then the protocols just change, the protocols of treatment just change because of this very, very small amount of cells that are left. How it works like this. In the diagnosis, almost all the cells are pathological, almost no normal cells, and after the treatment we have a few cells. We want to identify if there is pathological cells, if there are pathological cells or not, and if there are pathological cells, how many. We propose here a probabilistic approach for that. So the key idea is to try to establish a probability that a cell is pathological or the cell is normal after the treatment. How it works, I start building in a diagnosis file for each patient by mixing the disease cells, the neoplastic cells, with normal cells. Just remember that I said before, at the diagnosis phase, almost all the cells are pathological. So I have almost no normal cells. So when I say mix here, I mix in the computer. I just have the normal cells from donors, and the normal people are very, very, very similar. Normal cells are very similar from one patient to the other. So I can just have normal cells that are not from these patients and compare the cells with the pathological cells of these patients. So I mixed in these cells here in a proportion of 1:1. Why? Because I'm going to apply PCA. So I took a situation where the patient has almost no normal cells in there. I mixed with the pathological cells of these patients, and make PCA. This is based on the fact that the pathological cells, if they come back after chemotherapy, they will appear in the same area of the space. So I do this individually to one patient. So if this patient have some cells after the treatment, these cells would be more or less in the same area of the space. So I apply the PCA, and then I'm going to restrict attention to 2D because I want to see. And then I calculate the mean and the covariance matrix. I suppose normality, of course. And then I can calculate the distribution of X given normal. This means the PDF of an event assuming that the patient is normal, or the same thing for neoplastic. What I'm doing here is more or less that. But the problem is that what I really want to know is not the distribution of X given normal, but in fact I want to know the distribution of normal given X. X is a measure of the patient, and I want to know the probability of this cell to be normal or pathological. What we use it here, we simply apply the Bayesian theorem. The Bayes theorem, and then we inverted. We had before the Px given normal, and now we have the P normal given X. And here, the last problem is how to estimate the a priori probability, that's the P normal, and we have a specific iterative procedure for that. Now I have to test if this works. This is all real data, it's not theory. It's real data. So how we're going to test this? I have a file with 5 million normal cells for normal donors. Normal donors in some volunteers donors is something that in some laboratories is very dangerous, because people just approach you and say you are not very occupied now. Say yes, and then can you give you my blood? And this is in some places very dangerous, just to say you're not very occupied. And then when we write the papers, that's 5 normal donors, volunteers, and so on. And okay, so those are the volunteers, 5 million cells. And here I have the 50 patients this way. From each patient, I just took randomly in the computer, of course, different quantities of pathological cells, 1, 5, 100, and so on. And then I have files, and I end up with, for each patient, 88 files generated this way, that are a controlled mix of normal and pathological cells. So I have in the computer files that I know exactly the proportion of normal to pathological. And I'm going to submit these files to my algorithm. And the results were very nice indeed. In 80% of the cases, 40 from the 50 patients, the method was able to detect just 1 cell in 5 million. This is a very hard problem, because in general, what is considered by the medical doctors now that should be seen is about 30 to 40 cells in 5 million. So they are interested in detecting 30 or 40 cells in 5 million. And the method was able to detect in 80% of the case just 1 cell in 5 million. And then we calculate the R2 to see the level of agreement, and in 90% of the patients, 45 of the 50, the correlation was 9999. Okay, I'm going now in a different problem. It's the what we call differential diagnosis. Now I'm concerned with lymphomas. Basically, up to this point, we are talking about leukemia, and then we go into the lymphomas. What is differential diagnosis? I don't want to say if the patient has a disease or not, because this is an easy problem from the data point of view. What I want to say is that once I know that the patient has a lymphoma, which lymphoma is this? Because this changes completely the treatment. And this is a much hard problem, because the lymphomas are much similar among them. So what we call differential diagnosis is not worried if the patient has a disease or not, but I want to know which lymphoma they have. And those are the names of the in this project we study 8 lymphomas, and those are the names: BL, CD10 negative, and so on and so on. Just to give you the names that they're going to appear in in the figures in the next slides. We are working basically with 30 attributes, and we propose some different approaches for that. This is a project that we're still working on it, and but we have been working on it for the last 4 or 5 years. This is the first, not chronological, but it's the first of the approach. Is a tree classification approach, and the idea here is to differentiate one disease. HCl is one of the diseases. It's an easy one, and from all the others, and then from all the others, I subdivide in the BL and all the remaining ones, and so on and so on and so on, up to the point that I end up with the diagnosis. The good thing of the tree approach is that I can explain why, I can see all the way, and I can give multiple diagnoses. Because one thing that we don't want here is the false positives. So I prefer to say this disease is that or that, than to risk myself saying that this is that, but it was not. And this is real data again. Is the example is one example of the tree with the different diseases, and the tree comes all the way, and the results are very nice. This is in sample results. I will show the auto sample results in the next slide. A key problem here is the selection of the attributes, because the attributes are the antibodies, and I start with 30, and I have different selection of attributes in each node of the tree. And this is a key issue, and it's very interesting because once I have different attributes in different nodes, this means that I'm working in different spaces in each node. As I said, this is very important not to give false positives, so I use this region of uncertainty. Everything is done in the tree using logistic functions. So if I really don't know if it's the disease red or blue, I may give an uncertainty disease and stop the tree in that point. Those again are real problems. Just remember that a few slides ago I said that in one part of the project we work with all the cells, and another part of the means of the mean by each patient. In this case, we are working on the means. That's why you have so few points in here. In this case, each point is a patient and not a cell. Why we are working on the mean? Because in this case, I want to differentiate one patient in relation to the other patient, and not inside or all the cells inside the same patient. Those are the results out of sample that are very nice. And just notice here that we have possibility of multiple classifications. This means that I'm saying that is a BL or another thing. The second approach is a 2D projection. That's why I talked so much about projection before. And we use optimization criterion in trying to make the sets well split in the projector space. And those are the results that we have for the same problem, for the same data, or for almost the same data. I think that most of these patients, again, this is real data, and it's one patient per ball. One important thing in here that I didn't say is that just notice that we have here one disease versus another disease, one disease versus another disease, just 2 by 2. On the third approach, we are going to break this, and we are going to separate directly, using again as in projection, but separate directly from the 8 diseases to the diagnosis. So in the third approach, we are going to project into D again. And the cost function is going to preserve the distance to the pre-established prototypes. It's what I said after the PCA and the MDS. So the problem is supervised in the sense that in the training set I know the diagnosis, so I can establish prototypes in the high dimensional spaces. I project the prototypes on the 2D, and then I project each patient to the 2D space, trying to maintain the structure of distance between the patient and the prototypes. And furthermore, we use here, we estimate a probability function in the 2D space of observation in case a patient to belong to one class or to the other. By doing this, I can use a threshold, a cut, and say if the probability is too low, I just exclude this disease. And with this, I'm going to create a sort of hierarchical classification, because every time I exclude, because the probability is too low, I take the disease out of consideration, and then all the procedure in the end is going to be, in some sense, hierarchical using this probability structure. And again, the probability estimation, the probability estimation function is possible because we project in 2D. Because to estimate probability densities in 30 or 40 dimensions, it's in practice impossible. Again, an important thing is that we reselect the attributes in each comparison that we make. So there is no set of attributes that is good for everything. So since the procedure is hierarchical, I can reselect the attribute in different comparisons. So I look for more favorable attributes in different comparisons. And this is a practical, there is a small film in there. I think it's, this is a practical case. So we start with this. Dá uma paradinha, só um instantinho aí, dá pausezinho, só para, okay? I'm just going to explain how it is this table, this figure. This again is real data, projection into D. Each point is a patient. This is the point that we want to predict, we want to give the diagnosis. And this is the first situation. Here you have the 8 diseases, and they are represented in different shapes and colors inside this figure. And you can see that here you have the diseases that I know already that this patient is not any of these 3. Because, why? Because I have the probability structure in this space, and the probability of being from one of these 3 diseases is very, very, very low. So I just use the cut and take it out. At that point, what's going to happen? I transform the problem of 8 possible diseases in a problem of 5 possible diseases. When I do this, the problem is much more simple, and it's much more simple not because I reduce it from 8 to 5. It's much more simple that now I can give the diagnosis in a different space. I can choose different attributes. And it's much more easy to choose attributes for these 5 diseases than to choose attributes for the 8 diseases. So I go into a more favorable space to take my decision. And this is going to... Pode rodar agora direto. Oh. Esse era o primeiro? Pode rodar o outro. I have, I think, 4 cases in here. This is a different problem. This is an easy one. In the first plot, this is clearly this disease. It's a HCL. It's an easy disease, hair cell. And you know, here I have the probability of I cannot see it from here, 0.9 something. So this on the first plot, I went directly to the diagnosis because it's a very easy problem to give the, okay. The third one, No, this is the one we saw already. This is the third one. I asked the new partition here. This is working this way in the software. And then I go to this situation, and now I'm restricted to two diseases. All these are impossible. And then, stop, dá uma paradinha agora. This is it's a very interesting case because I went into just between these two diseases, and it's almost impossible to give the diagnosis. So what I'm going to give as an answer here is a double diagnosis. Could be this or this, and I don't know which of the two. This is exactly what the medical doctors want in this sort of problem. Just don't risk yourself saying that the disease who has the highest probability is the one. They prefer to give the double possibility. And this is clearly the double possibility. And I can give not only this, but I can give to the medical doctor exactly the plot. That's what I called in the beginning. The decision is taken by the user. So the medical doctor is going to take the decision based on that. What I'm saying is that could be that on that, your patient is here, and that are all the other patients, and you take your decision. Okay? This is a different case. We start here. It's not so easy. We just exclude the CLL, but we have all the other 7. We should press here. And then on the other plot, dá uma paradinha aí, por favor. Parou aí. Notice that on this plot, it's very interesting because a problem that on the previous plot looks like a very difficult one, and it is a difficult problem, was just transformed in an easy problem because I just excluded the 6 and just come to just 2 diseases. Why it so suddenly came from A to 2? Because I'm making this in a different space. I could choose different attributes, and because of these well-chosen attributes, I'm able to transform the problem just in 2 possibilities. And then we're going to see a plot of just BL versus CD10 positive. And in this case, I just have the 2 diseases here, and clearly is a BL. You have the probability here, and apart from the numerical value of the probability, I can give the medical doctor the plot saying that your patient is here. So I'm saying that the probability of being a BL is very high indeed, and you can compare your patient to the other balls that are the BLs. The balls are the BLs, the crosses are the CD10. And not only I'm giving the diagnosis here, but I'm showing the plot, I'm showing the patient in comparison to all the others. And I think it's the last chapter or so. Coincidentally, I want to go a little bit on the previous panel and talk a little bit of, in this case, what happened from the academic research to the real-world application in this case. And we start publishing. It's quite important to publish, of course. And those are some of the papers of part of the work that we showed before. From this part, we go to innovation. This means patent. And Boisson is not here, so I can tell bad things about him now. I will, in some sense, disagree with something that he said in here, because he said that we should use patents and not papers, or patents are more important than papers. I think both are important. And in X, he said most of the papers are not cited. And worse than a non-cited paper is a non-licensed patent. And more than 90 or 95 of the patents, registered patents, are not licensed to any company. So the patent is only important if one licensed the patent. Otherwise, it's worse than to have a non-cited paper. And here, I said that it's, I'm going to make a propaganda of BD back to this. It's not in the area of Microsoft, so I can talk about them. And these patents are licensed to the BD. What's the same company on the first slide that put on the market the first cytometry about 40 or 50 years ago, and it's probably the biggest in the world. So this is licensed. And the more important of everything is this is more important than patients, and I'm very proud of that. This is in real use in all over the world, in more than 50 countries, because this work that came to the innovation came to a software. It's a commercial software, and this is real used in 50 or more than 50 countries in the world, giving real diagnosis on lymphomas and leukemias. And I think this is the important part. Is the end of the thing. So. I still have to give a last part of what I promised. I didn't deliver the future perspective, in my view. This is going too fast. I'm not going to stop it. No. Can I stop it here? I think. And these are the things I think, in my view, are the future perspective to quantitative methods in medicine. I think that, again, data mining tools are going to have more and more importance. They are going really to play a key role in the next decade in these sort of problems. The second thing is that information should be made available for user. In our case, we are using 2D projectors, but it's very important to think in methods that not only give the solutions, but made the solutions available in an easy, possibly graphical way to users. And the third point is that I think the avalanche of medical data that I talked on the very first slide is going to continue. We are going to see more and more medical apparatus, more data, and we have to be able, we of machine learning area, have to be able to process this data in an intelligent way. And finally, I put in a different slide because I think it's very important. I think these problems have to be solved by a new generation of professionals that should work together from different areas: engineering, statistics, computing, machine learning, and so on and so on. At that point, probably you know already the name of my chapters, where they come from. So let's come together. And part of the cytometry work that I shown here are part of our collaboration with the Euroflow Consortium and with the lab that we have in the Children's Hospital of our university. And another chapter. I don't have all the technology for the photographs that we saw before lunch. This is the Euroflow group in a meeting in Prague, I think 2 years ago. And those are my main collaborations. Some of them are around there. Laura is taking a photograph of her name in there. Okay. And we can work it out.
Thank you very much, Professor Pedreira, for that great talk. I think we have some few minutes for Q&A. So, any questions? Francisco Cantu.
Thanks for the presentation. That reminded me a course I used to teach on pattern recognition some years ago. But the question is, I think I saw at least 8 green slides with Beatles songs on it. Is that the case? I think, I mean, I like the structure of your presentation with yesterday, get back, here, there, and everywhere, the long and winding road.
Please don't think.
Let's get together.
Please don't think. Yeah, just names.
And so the comment is that, well, it kept my attention. So I like the style of the presentation. And this is the first question, the first comment. Second is about the false positives and false negatives. So you didn't talk about the false negatives in the presentation.
Okay. In this sort of problem, it's very important to take attention on the people who are making the questions. And the people who are putting the question here are the medical doctors. So what they said to me, this is a straight collaboration that we have with the University of Salamanca and the Euroflow group, and that we don't want false positives in the sense that we don't want to give to the doctor information that this disease is that and it's not. I prefer to give the disease is that or that. So false positives in the sense that I prefer to give a doubt as an answer, a double reply, than to risk myself in a diagnosis that may not be true. And it's important to take into account also that I give the double reply, but in the graphical mode, I also give the graphics. So if the medical doctors are looking at, no, you gave me that this could be A or B, but for me, in this case, it's clearly A. Okay.
We have time for one more question, please.
Hi. My name is Roseanne. I'm from University of São Paulo, working for many years in multidimensional projections. So, hey, great. Can you get back somehow to your papers slide? The slides you present your papers. What? The slide you present the papers you published.
If I can,
is it possible?
Can you put a slide of the papers?
Oh, the papers, yeah.
Please.
My question is there. One. It's very quick.
They're doing it.
Deve ser o 7º, 8º de trás para frente.
É um dos últimos. Antes.
Can you start with the question while he's looking for the slide, please? Or?
The other question I have is your data, have you published your data?
I didn't publish the data. I published the results.
Okay.
The data belongs to the Euroflow group.
Right.
And we publish everything in the papers and in the patents, so everything is fully public in this sense.
Even the data?
The data is not published on these papers. The data is going to be made available by the Euroflow, I think, in the next month or so. They are revising all the data, and the data is going to be available.
Great. The second paper over there, Automated Pattern Guide, the Principal Component versus, who won?
The automatic guide, the PCA is better.
Okay.
Yeah.
That's a very nice piece of
Yeah,
information.
the PCA, yeah.
Okay, thank you.
Thank you. Okay, thank you so much, Dr. Pedreira. Let's thank Dr. Pedreira for his great talk.